Okay, so now we want to get to how skewed are our data. Remember that, bear with me here. Okay, so remember that our earlier data proved to be, quote, normal. That is, bell shaped, symmetrical, mean, median, mode are all the same. And so this looks like that really nice looking bell curve. So then I presented you, though, with those two extreme cases. And where are we here? We had these two. So how skewed are our data? We've got the average age of all executive coaches, and we've got two newbies or two youngins. And so we think, wow, that's really kind of, quote, skewed. That doesn't seem normal because most people typically, when you think of executive coaches, would probably be somewhere more in this kind of range. So you think, okay, well, how skewed is my data? And by the way, what this means is that you have a left skewed data set. And specifically on page 57 and 58 are nice depictions of non-normal data or shapes, non-normal shapes. That is left skewed shape and right skewed shape. This is left skewed because there are some extreme data sets or data points that are on the low end. So if you look on page 58, panel A represents this kind of data set because there are two extreme data points here. That is exceptionally young, crazy executive coaches here. So then you're trying to think, well, how skewed are my data? Okay, so if we took, this is very cool here. So if we go to data analysis, we choose descriptive statistics, hit OK, and then let's fill this in again. A2 through A10, you can see those are the values here. And we put even summary statistics, confidence level for the mean, which we'll talk about later, and hit OK. Now we get to figure out how skewed this data really is. And I basically redid this here. What's cool about this is you see once we chose descriptive statistics, which is why I had you download the analysis toolkit, is that you've got the mean, the median, the mode, standard deviation, the minimum, the maximum, and the range, the number of data points. It's all there for you. So I love this descriptive statistics choice. Now, left skewed data is when the mean is less than the median. And that means that the average is lower than the middle of the data set because there are some extreme values on the lower end that pull the mean down. So if you notice, the mean, 50, is less than the median, the middle of the data. And notice even the most popular number, 62, which is way different than the mean because those youngins made the average too small. So then you look at what's called skewness. This is how skewed your data is. And you want to know this because you may have to do a different statistical look at this data depending on what you're trying to do with them. One way of looking at skewness would be just a box and whisker plot that is noted in one of these chapters that I had you read. Or you could do this basic kind of statistic that I've just shown you. And to be sure, here is a general rule on skewness. If skewness is less than 1 or greater than 1, the distribution's highly skewed. If it's between -1 and -0.5 or 0.5 and 1, the distribution's moderately skewed. And if the skewness is between -0.5 and +0.5, the distribution is approximately symmetric, meaning this means a normal distribution. So normal distribution and otherwise skewed. So in this case, if you look at the number that we had, it was -0.85, which is between -0.5 and -1, which means it's moderately skewed, which frankly might make intuitive sense for you. Now, let's see if I did this for the next one. Yes, so what I did here is I took it to an even bigger extreme, just to prove the point. So what if we had the same people here, but we made the youngins even younger? Say we randomly had an executive coach who's 10 years old, some child prodigy, and another one who's another child prodigy who's 12 years old. Clearly, if we got 9 people and we had two child prodigies, that's weird. That's, quote, not normal. It's skewed. So if we ran the same analysis, just using data analysis and descriptive statistics, this is what we get. So notice the mean is even lower. Before it was 50, now it's 47. The median and the mode stay the same. And your skewness is now negative 1.1, which is less than negative 1. So you're in the highly skewed, which frankly, again, I hope you know makes a lot of intuitive sense, because if you literally collected this data, 9 people, and you got 2 child prodigies, you too would naturally know that there's something askew about this. Okay, so that's one way. And again, the skewness is a nice to know. Most of you will probably not ever have to deal with skewness, but if you do, there are different statistics that you may have to run. But I think it's important for you to understand the nature of the data just to see what we're dealing with. Okay, so now let's get back to this graphic that I showed you, this figure. If you remember during the residency, I was talking about how the goal is, when you're dealing with quantitative and mixed method studies, they are deductive, right? So you already have a grand theory that you've postulated. And now the question is, how can you measure it? So as one example, we might decide that taller people are better coaches. So the taller you are, the more effective you are as a coach. So that's your grand theory that you've deduced somehow. And then notice that the deduction or deductive theory suggests that what you can then do is look at a single individual and say, how tall are you, and make inferences about or conclusions about how effective he or she will be as a coach. Are you tall? You're going to be good. Are you short? Not so good as an executive coach based on your theory. But you have to be able to take your theory from something super abstract and break it down to something measurable. So that's the goal of statistics, is to create numbers or identify numbers and label them in like surveys, for example, and make statistical or analyze the data statistically. So one thing that I will tell you is, remember, in one of the homework questions was, is education in the personal psychology article categorical or numerical? I think a number of people got tripped up here because a lot of people said numerical because each category was assigned a number. In fact, when you think about how anybody taking that survey would have looked at that education, they would have been given different categories. Did you get a doctorate? Did you get a master's degree? Did you get an undergrad? And they would basically check the box, so to speak, next to that category. The only reason there were numbers assigned is because the authors of that paper, that is the researchers, assigned numbers to the categories for the purpose of statistical analyses. So education was categorical because the variable is basically measured in terms of different categories. Okay, so our goal again with all this quantitative stuff is to get data that is numerical, that represents these bigger concepts and theories. Okay, so now let's get to this notion of sampling distribution and central limit theorem. These are nice to know things. I would say I'd like you to know them, but they're not 100% necessary to keep moving forward. So say we're trying to make conclusions regarding all executive coaches, and I asked each one of you in the class to go out and get a sample. Say each of you had to sample 20 different people on something, like how satisfied are you in your career, 1 being totally unsatisfied and 5 being satisfied. It may well be that Alex's average, his mean is a 3, and Nancy's mean is a 4. So, and that wouldn't be that surprising. So we could collect any number of samples and they might look different. So one sample of 200 coaches might have a mean with an average age of 50 and another has a mean of 48. So the question is, does this make us fret? This is the notion of what's called sampling distribution. That is, if we collected a lot of different samples, there would be a distribution of sample means. That means there would be some that would be on the low end of the mean, lower than the mean. Of all of them, if you averaged all of the means, there would be some that are lower than the mean, and some that would be higher. But statisticians have developed this notion of the central limit theorem, so we don't get stressed out that we only have collected one sample to represent an entire population, which is essentially what we do. So it states that if you have a large enough sample, your distribution becomes normal. So there are a lot of different things here going on, one of which is collect big samples. There's a reason that people consider big data sets sexy, and that's because it helps statistically to become more conclusive. Okay, this notion of sampling error. Sampling error is the variation that occurs due to selecting a single sample from a population. So the idea is because one sample may or may not represent the true population it's intended to, we have this notion, the variation that occurs due to selecting a single sample. So as an example, a popular one, and the book I believe discusses this, when we do pollsters for political affiliations, for example, or anything political, there's always the plus or minus error in there on the bottom right hand of the TV screen. So it might be something like 60% of all Democrats approve of Obama's performance, and in the bottom right hand of the screen it reads plus or minus 3, meaning that it's likely the real interval is somewhere between 57 and 63%. So plus or minus, we get a little variation because we're not sure, because we've only selected one sample. So to account for sampling errors, statisticians have developed the notion of a confidence interval, which essentially creates a range within which you can be fairly certain that the real population falls. So a confidence interval estimate is an estimate of a population parameter stated as a range with a lower and upper limit with a specific degree of certainty. So as an example, 57 to 73 or 57 to 63% we can be 95% sure that if we collected all means on Obama's popularity, that 95% of them would fall between 57 and 63% in terms of people liking him. I didn't state that very well, but I'll keep continuing to state it. So a 95 confidence interval estimate means if all possible samples of the same size were selected, 95% of them would include the population parameter in them. So if we collected 100 samples on executive coaches, and they were all 20 people in the sample, then if we gave an interval of, say, 100 to 200, 95% of those samples the mean would fall between 100 and 200. And unfortunately, 5% of them would not. Page 106 in your book does a nice job of describing this.